Okay, so we're going to do the periodic trend notes. And these were from Thursday, November 3rd. So what we're going to be talking about is trends on the periodic table due to the valence electrons. So the valence electrons go from S1 over to P6, and the periodic table has certain trends that move from left to right due to that. And then the other trend on the periodic table is 1 energy level, and then down to 7 energy levels. And so there are periodic trends that go along with the increasing energy levels. So we're going to look at periodic trends that are associated with these trends, S1 to P6, skipping the dip, skipping the transition metals because those are not the same, because they have that D and F in there. So we're only going to be talking about the S's and the P's pretty much. And then we're going to go from 1 to 7 down top to bottom. So those are the trends that we're going to be looking at, left to right and top to bottom. So the first trend we're going to look at is something called atomic radius, which is defined as the center of the atom to the farthest electron. Center of the atom. So from left to right, this trend is that the size of the atom or the element decreases. From left to right, it decreases. And the reason that this happens is because there is an increasing positive charge in the nucleus, but the energy level remains the same from left to right. So moving, if we look at, say, the 4th energy level as an example, so N equals 4, just as an example, going from potassium over to krypton, as an example, we're piling more protons into the nucleus. So the number of protons increases. But the energy level, number 4, stays the same. And so what that means is the electrons aren't getting any farther away from the nucleus. They're not getting any farther away, but the number of protons in the nucleus is increasing. We call this like the effective charge, the nuclear effective charge. And that is increasing from left to right because the number of protons, the positive charge of the nucleus, is increasing. But the electrons surrounding it aren't getting any farther away. And so what's happening is they're getting pulled in closer and closer and closer because the power of that nucleus is getting greater and greater and greater. So the size of the elements as we go left to right are getting smaller and smaller and smaller because the power of that nucleus is getting greater and it's pulling those electrons in tighter and tighter. But then top to bottom, from top to bottom, we are increasing the size of the elements. And the reason that's happening is because every time we go down the periodic table, we're adding an energy level. So from 1 to 2 to 3, we're adding an energy level, and that is causing the size of the element to increase every time you go down. So for example, from hydrogen to lithium to sodium, we're adding an energy level as we go. And so that being the case, the electrons are much farther from the nucleus each energy level, and the pull into the nucleus is decreased. And that's going to be super important as we go on, that the farther away from the nucleus the electrons are, the smaller the pull to the nucleus is. So increases left to right, decreases left to right, and increases top to bottom. Next, the next trend that we're going to talk about is ionic radius. And we're really talking about within an atom, not generally across the periodic table. We're talking about within an atom. So we're going to look at the octet rule, which we've already talked about once, but let's put it in our notes again. An atom will gain or lose electrons in order to have a full octet. And the octet that we're talking about, as we described before, is the S2 and P6 electrons. So if an atom, an element, was to lose electrons, it would become smaller. Why is this? So I'm going to box this in a different color because we're about to write a lot of words here. So it could get lost. And since we actually are talking about the trend, we want to box trend. So losing electrons, it becomes smaller. And if it loses the electrons, the atom will have a positive charge because it lost that negative electron. Now, why does it become smaller? Well, let's take a look. So I'm going to choose beryllium as my example, which is 1s2, 2s2. And so to become full, which is what beryllium wants most out of everything, beryllium is going to lose these 2s2 electrons. So beryllium has because it wants most in life to be like helium, which is 1s2. And if it's like helium, it'll be like the noble gas. It'll be like the cool kids, right? So beryllium has 4 protons and 4 electrons. So what's going to happen is beryllium is going to lose 2 electrons. They're going to go away. These two, the 2s2 electrons, are going to be gone. And when it does, it'll be 1s2 like helium. But the thing is that when it loses those 2 electrons, these 2 protons will be by themselves. Like they won't have 2 electrons to neutralize them. See, these 2 electrons and protons neutralize each other. And without those 2 electrons, those 2 protons are sitting out there, without any electrons to neutralize them. And so that gives beryllium a 2+ charge or a +2 charge, whichever you feel more comfortable with. So 2 protons are left unneutralized. So that's what the 2+ is about. But why is it smaller? Well, the reason that it's smaller is because, first of all, you are emptying that second energy level. So it's lost the entire second energy level when it loses those 2 electrons. So you're emptying an energy level. But the second reason also is because each one of these electrons is repelling the second electron, the other electrons. So they need a certain amount of space, these 4 electrons need a certain amount of space because they're repelling each other. They can't willy-nilly just sidle up to each other and like be right next to each other. No. They need a certain amount of space around them, right? And then what happens is when there's less of them, they need less space. So you need a certain amount of space for 4 electrons, sure. But when 2 electrons are gone, you need less space for 2 electrons because they don't have to repel 4. So they only need to repel 2. So now the actual size of the atom can be smaller. So even if beryllium was only going to lose 1 electron, it would only need to have space for 3 electrons repelling each other, not 4. Okay, so gaining electrons, it's going to get bigger. It becomes larger. So why is that? So let's box this because that is the trend, and we are trying to isolate that trend since that's the whole goal here. And when it becomes the larger, the atom will have a negative charge. Okay, so why does it become larger? Well, let's take a look at fluorine as our example. Fluorine has 9 protons. Oh, sorry, it's 1 S2, 2 S2, 2 P6, 2p5, sorry, 2p5. All right, so how many electrons does fluorine need to be full? It needs 1. So fluorine has 9 protons and 9 electrons. And it's going to add 1 electron. So there it is, because it needs 1. So that's going to make it P6. There it is. And here's that 1 electron. So all these electrons are going to cancel out, except for that one. And that is going to cause fluorine to be F minus. So there's that charge, meaning that it's going to have a negative charge. So there it is, the F minus. That's the 1 electron that doesn't have a proton to cancel it out. And it has 10 electrons. And so what size is it going to be? It's going to become larger. And why? Because the repulsion between the electrons, remember these electrons are all repelling each other. Now we just added 1. That repulsion is going to push it farther away. And so those 10 electrons are going to need more room than 9. Our third trend that we're going to talk about today is ionization energy. And ionization energy is the amount of energy that it takes to remove the last electron put into the valence electrons. All right, so it's the last valence electron put in. And this is the amount of energy that you have to use to overcome the attraction between the nucleus and the electron. This is directly related to the size of the atom, directly. So the smaller the atom, the element, the higher the energy. So this is opposite from the atomic size. So as the element gets larger, the ionization energy gets smaller, and as the element gets smaller, the ionization gets larger. Therefore, left to right, the ionization energy generally increases. And the reason is because it's due to the atomic size decreases. And due to the increase in nuclear charge. So this is all about the atomic size. As those protons are put in and that nuclear magnet increases, those electrons are held on more tightly, and it's going to take more energy to pull them off. Top to bottom, the amount of energy needed to pull those electrons off is going to decrease. And that's because the atomic size increases due to energy levels being added, and so the electrons are farther from the nucleus. So if the electrons are farther from the nucleus, then the pull to that nucleus is less, and it will take less energy to pull off that electron. Now, the second ionization energy, which is the energy to pull off the second electron, is always higher than the first. Because even if you're getting closer to stability, meaning like I have to pull off 2 electrons, like here, beryllium, I want to pull off 2 electrons to get to be full. So you'd think, oh, well, once I pull off the first one, the second one might be easier because I'm going to get to be helium, right? No, but you're still dismantling that atom. And once you pull off that first electron, the same nuclear charge is now spread around 3 electrons, not 4. So that third electron is now being held on by more charge than the 4 electrons were, more charge per electron than the 4 electrons were, right? So now the ionization energy increases for that third electron over what it was for the fourth. So the second ionization energy is always higher than the first. The third is always higher for the second. But one thing that is important to note is that once you remove the electrons that need to be removed and you're down to the stable electron configuration, then the ionization energy is going to increase about 10-fold to pull off that P6 or that S2. So in this case, the first ionization energy for beryllium will be high, will be, what it is, not so high, because, pulling off the S2. The second ionization energy to pull off the S1 will be, a little higher. But then to pull off this S2, it's going to be 10 times higher because the beryllium is stable. Okay, so, and that's what would do in the graph. Like your homework tonight that's what it is showing this. All right, in question 4 and question 6, they're talking about why is the ionization energy so much higher? Because you're pulling off that stable P6 or S2. But the second ionization is always higher than the first. And noble gases have high ionization because why? Well, they're P6. They're not going to bond with anybody. They're not going to give up any electrons. All right, so you're not going to graph the first ionization energy. We don't do that anymore. But you are going to do the first, second, and third ionization graph, and you're going to answer the questions. So that is the next link. The next module, it has the explanation for that, and there is the homework assignment graph paper, and then a video showing you how to do it.